And so, yeah, so a priori, this kind of looks like quite a different topic to what Daisuke was talking about. And yeah, in many ways, it really is quite a different topic. But yeah, as you mentioned there, actually, one of the things I'm interested in is sort of random walks on random graphs and in random environments. And actually, there's kind of a nice general theory, of course, about electrical networks and how these can be used to describe various properties of random walks on graphs, should we say. And yeah, actually, it turns out that studying the scaling limit somehow of the resistance as a metric turns out to be, in at least certain contexts, quite a useful way to understand the scaling limits of the random walks on the graphs that we're interested in. And so that's the kind of connection that connects the model that I'll be talking about in this talk and the one that Daisuke talked about. And so, yeah, just to kind of connect a little bit more strongly, actually, here's kind of a result that Daisuke didn't mention, but which we can prove for the random walk on the uniform spanning trees in low dimensions. So, yeah, so in particular, well, Daisuke described how by viewing the uniform spanning tree in 3 dimensions, say, as a metric space, we can understand its scaling limit in a suitable Gromov-Hausdorff type topology. And well, we can do similar in 2 dimensions, where the sort of limiting objects, of course, relate closely to SLE type objects. So in particular, exactly the paths within these scale to kind of SLE2s, and so we get a tree of SLE2s, kind of where we can kind of, I suppose, build it as via a continuum version of Wilson's algorithm, I suppose. But anyway, so we can understand the scaling limits of these trees as metric spaces, and actually there's various results in the direction of studying random walks on the scaling limits of random trees. And yeah, so I mean, I started working on this a while ago. There's a nice paper of Athrea, Learn, Winter. I think a couple of them are in the audience today, where essentially they show that if we understand the scaling limit of the metric on a sequence of graph trees to some non-trivial limiting space, and of course also well, the measures upon the trees as well, the sort of natural counting measures, say, on the trees, then we can understand the scaling limit of the random walks on these trees. And so it's kind of more or less a straightforward application of the sort of scaling limit result for the trees that Daisuke mentioned to conclude that we can also understand the scaling limits of the random walks on these objects. So yeah, maybe just to describe the result a tiny bit in more detail. So yeah, so XU is just here the usual simple random walk on this graph. And yeah, so under the annealed law, so this is where we average out over the law of the random walk itself and over the law of the tree. It turns out that if we rescale the random walk in an appropriate way, so we're scaling down the lattice here by 1 over n, and we need to rescale time in a certain way that's, of course, depending on dimension here. So, of course, this is quite different to the usual diffusive scaling that you need for simple random walk on the lattice, where the time scaling here would be n squared, sort of independent of dimensions, of course. Here, kind of the walk is constrained by the geometry of the tree, and so we need to kind of take this number that's actually bigger than 2 in both these cases. And actually, this is just the dimension plus the growth exponent of the random walk in each of these cases. And so, well, I guess if someone's interested, I can explain why that's the right exponent later on, maybe after the talk. But yeah, that's the kind of exponent that comes out of the argument here. And yeah, it turns out that if we rescale in this way, then we can arrive at some natural diffusion. And so there's, yeah, so this is kind of an abbreviation of the results that are proved in these papers here. Somehow, naturally, this diffusion is defined on the abstract tree that's the limit of the uniform spanning tree. And we also then need to somehow embed that tree into Euclidean space. And somehow that embedding is non-injective, so it's not quite so easy to describe in Euclidean space directly. But anyway, we can arrive at some natural continuous Markov process in the limit when we scale like this. And so, like I say, the basic conclusion about the random walks here follows from some quite nice general results about the scaling of sort of metric space trees and the stochastic processes on these. And the reason why that kind of result works is because exactly kind of as I mentioned at the start of the talk, this kind of connects very strongly, particularly in the tree case, to the view or the association of the random walks and electrical networks. And so in particular, the metric on a tree is, of course, just describing the electrical resistance on the network. If we're kind of, instead of, well, if we're viewing this as an electrical network where we're putting kind of resistors of unit strength, say, on each edge, then of course the graph distance between them is exactly the same as the effective resistance, just by the sort of series law for resistances. That's what you get in this case. And so somehow this knowledge of the resistance is completely kind of characterizing the behavior of the random walk. And so then it's not so surprising that when we kind of view it like this, that somehow understanding the scaling limit of the resistance, as we do when we understand the scaling limit of the graph distance, tells us something about the scaling limit of the random walk. And so that's in essence why these kind of abstract results about trees really work as they do. And so yeah, later on in the talk I'll mention a sort of slightly more general version of that result for where we replace the sort of graph distance on trees with effective resistances on graphs. And so that's going to be the version of the result that's going to be useful for the model that I care about. Yeah, maybe just one other comment. So Daisuke also mentioned actually the transition densities of the random walks on the uniform spanning tree. Actually, again, because of some nice connections between electrical networks and random walks, it turns out that somehow the heat kernel or the transition density of the walk has kind of nice continuity properties when we look at it with respect to the resistance distance. So and actually we get a bit more than this. So not only do we understand scaling of the processes, we'll also understand things like scaling of the transition density of the discrete object to a natural transition density of the continuous object, and other things like mixing times as well converge nicely as well. So of course for mixing times we need to look at sort of, I guess, finite sections of the tree. But anyway, so from this kind of viewpoint, we can understand various other aspects of the random walk on the tree. Okay, so anyway, that's the kind of connection with Daisuke's talk. As for my talk, the model is quite different, and so if you kind of just, I guess, joining late or waking up, then you can kind of join fresh at this point. So yeah, so unlike Daisuke's model, which is quite challenging to even define in the sense of we have to take some infinite limit of uniform spanning trees on boxes. Here I have a very simple model. And so my basic environment is just going to be given by the points of a one-dimensional Poisson process on the line. And so these are these points omega here. And just to kind of fix a starting point for my random walk, I'll just insist that omega 0 equals 0 is included in the set of points here. And so that's my environment. And what my process is going to do, this is going to be just a continuous time random walk. For simplicity, I'll think we've just got jump rate 1, so we just have exponential holding times. So kind of something like the discrete time random walk. And the effect of the random environment is just going to be seen in the transition probabilities of this walk. And so in particular, we jump proportional to conductances of this form here. So somehow the conductance here is decaying exponentially with the distance between the points in question. So I should say this is just for points I not equal to j here. Okay, and well, for a Poisson process, it's not a difficult exercise to check that the sort of total sum of these conductances out of a vertex is finite. I mean, the distances are just growing sort of linearly with the distance between I and j, and so this thing is finite, and so this walk is well defined. Yeah, I should say other people, like, and maybe from the physical point of view, it's maybe a little bit more natural to think of just the jump rate from I to j as being given by the conductance directly here. Of course, that just changes the holding times. So rather than jumping at rate 1, we jump at total rate equal to this out of the site. But actually, for what I say, both of those choices will give basically the same long-term behavior. And yeah, maybe just as a little bit of motivation. So there's kind of some physical reason for studying this walk. So the name is coming from Neville Mott, who was a Nobel Prize-winning physicist in the 70s, who was using it to study electron transport in non-crystalline materials. So if we kind of go back to this picture here, these Poisson points are meant to represent somehow, well, the picture is meant to be at low temperature, and these points of the Poisson process here are meant to represent electron localization sites. And well, in his work on sort of semiconductors, he was interested in how electrons move between these localization sites, and the kind of factors that were described as being important were the sort of spatial separation between the points, and also somehow an energy separation between the points, and sort of a little bit more generally than maybe the models discussed there, or maybe less generally, I guess, in certain aspects. We could kind of generalize the picture on the previous page to conductances of this form. So maybe you've got sort of the distance here. Possibly you might want to generalize by adding in some distance exponent here. So I'll maybe briefly discuss this factor at some point in the talk. But like I say, also other factors that are physically relevant are things like energy separation of the site. So each site in practice might have an energy mark, and we've got some function that describes how the conductivity depends on these. In this talk, I'm going to actually just set beta to be 0, so I'll ignore this. So this is just, well, so beta is the usual inverse temperature in statistical physics. I'll just ignore this. But in our main result, we could include some term of this form if we wanted. I'll just kind of miss it for simplicity. And finally, as well, we've got kind of a drift term here. So this is kind of like having an external electrical field kind of with a particular direction imposed on the system. And so again, in this talk, I think I'll miss this out, but we can allow some version of this in our result if we wanted. And so, yeah, basically I'll be focusing on this case here, where we're just looking at how the conductance depends on the distances. Yeah, I should say, of course, all of these definitions apply to sort of more general point processes in one dimension and also in higher dimensions. And so, yeah, I saw Alessandra Faginato is here, so I think she's done a lot of interesting work in kind of the high dimensional version of these problems, and also studied the random walk on other versions of point processes as well. So the Poisson choice is kind of just a simple example of a random point process satisfying the kind of properties that we're going to need for our results. Okay, so the basic interest is, of course, understanding how the system behaves as we vary these various parameters. And so here's just a kind of simple question to have in your head. So in particular, Mott was kind of interested in, like I say, non-crystalline materials. And so kind of to compare with a natural version of a crystal, we might want to think of taking some sequence of sites with the same density as our Poisson process. So namely just kind of rescaling the integer lattice like this. And of course, then if we take conductances of this form, so or more simply of this form here, then we just have a random walk with a finite variance. So of course we scale to a Brownian motion, and that's kind of very easy to check, of course. And the question is kind of what happens when we introduce inhomogeneity into the material. So we kind of perturb our lattice and kind of replace it by this Poisson process of the same density here. So yeah, I should say actually as well, like one other kind of minor point is that often like looking at one dimensions is quite unphysical, but actually in the physics literature, there are kind of papers studying the one-dimensional case. So we can of course think of this as like a wire, kind of a thin strip of metal, of course. So this is, yeah, there is some physical motivation for studying the 1D result in this case. Okay, so anyway, so here's what's known. And so, yeah, actually kind of interestingly, not only is kind of the alpha equals 1 case maybe the most physically relevant, it's also the most mathematically interesting, in that we have an interesting phase transition. So the mathematical results go back to Lise Caputo and Faginato in, well, about over 10 years ago now. So they observed that if we have kind of a suitably large density in our Poisson process, so rho bigger than 1, then we see just the usual diffusive scaling. So we scale by n squared in time, n in space, then we converge to a Brownian motion. And this is kind of in a very strong sense, in the sense that for almost every realization of our point process, then we converge to the same Brownian motion. And the only effect of the randomness here is just in the diffusion constant here. And actually in this paper, there's kind of more study on well, how to characterize this diffusion constant and how it kind of depends on the parameters and so on. But anyway, so in this regime, we've got so-called homogenization. We're seeing just the usual diffusive behavior. This is just the same as the lattice. The situation becomes a little bit more interesting when we kind of lower the density of the particles. And so in particular, when rho is less than or equal to 1, so again, just thinking about the alpha equals 1 case for a minute, then again, we can describe basically the same result as happening. But now actually the diffusion constant is going to be 0. So in other words, this kind of diffusive time scaling is kind of the wrong scaling for the walk. We need to kind of run the process for longer to kind of see some non-trivial limit. And so in particular, we're in this sub-diffusive regime. Yeah, I don't think I'm going to talk too much about the alpha not equal to 1 case in this talk, but yeah, somehow this just kind of exacerbates the problem. So actually, if alpha is less than 1, we're kind of more strongly in the kind of homogenization regime, and for alpha bigger than 1, we're more strongly in the sub-diffusive regime. And actually, we can describe what happens in that alpha bigger than 1 case, and we've done so in a kind of a very recent paper. But today, I think I'm going to focus particularly on this alpha equals 1 case, and the sub-diffusive regime for that. And so in particular, what our result says is that actually, if we rescale again the walk in an appropriate way, so in this case, if rho is less than 1, this 1 over rho is of course bigger than 1. So exactly, I've got more steps than the usual diffusive scaling here. And if we rescale in this way, then we can arrive at some interesting non-trivial limiting process. And so the point of this talk is just to briefly describe what this limiting process is. And so I should say that this is again a result with respect to the annealed law, so averaging out over both the process and the environment. Yeah, I should say it's sort of another kind of natural question, maybe just as background. So you can also ask what happens in the other dimension. So, and again, there's kind of nice work of Alessandro, which he studied these kind of problems. And so actually, in some sense, the result becomes less interesting in higher dimensions. So actually, in that case, then we always are going to see diffusive behavior. So we don't see this kind of interesting phase transition. And perhaps kind of as the talk goes on, it will become clear why the one-dimensional case is kind of special. And in particular, what we'll see is that somehow in this subdiffusive case, sort of the cause for this subdiffusivity is that we're going to find sort of some individual edges where, well, when the density is suitably low, we see some kind of nearest neighbors that are sort of suitably far apart for the conductance to be very small. And that's going to be enough to lead to this, well, somehow big resistance. And so this is going to lead to some kind of blocking of the random walk. And that's going to kind of persist in the limit and lead to this subdiffusive behavior. And somehow this kind of phenomenon is not going to happen in higher dimensions. You will see kind of isolated points in your Poisson process, but you'll never actually reach them by the random walk. And so that's the sort of difference between the one-dimensional and the higher dimensional case. Okay, so that's the kind of result. And so, yeah, I want to describe today kind of some ways to think about why this is the right result, and then secondly, kind of how we actually prove it. And so to think about why this is kind of the right result, I'm going to start by just looking at an even easier model. And so this is kind of going to be the same model, but I'm going to sort of delete all of the edges that are not nearest neighbor ones. So in particular, I'm just going to, again, take my Poisson process as before. And again, I'm going to look at the continuous time random walk, let's say jumping at rate 1 again. And so I'm going to have the same transition probabilities as before. Apart from now, I'm only going to allow the conductances to kind of be non-zero, even only if we're kind of nearest neighbors in my Poisson process. So I kind of rule out any other jumps. And so now my graph is really a one-dimensional graph. It's just kind of a perturbation of the integer lattice like this. So of course, the full graph is somehow the complete graph on the integers. Okay, so this is my situation. And to kind of explain what the limit is, I think it's helpful to kind of briefly remind people about the story of one-dimensional diffusions. So of course, this is a very classical kind of topic. And essentially there's two kind of properties that, or two kind of quantities that describe or characterize a one-dimensional diffusion. So these are the scale function and the speed measure. And so the scale function is a function that sort of describes the sort of harmonic properties of the walk, so the hitting probabilities of the walk, or the diffusion, sorry. And so in particular, the scale function is up to, well, a constant multiple, I suppose, characterized by this formula here. So in particular, if we start at x, the probability of hitting z, say, before y, can be described in this way. So of course, for the usual kind of Brownian motion, this result is true where s is just the identity. And well, if s is, well, in the sort of more general case, then actually if we just rescale our diffusion by the scale function, then actually this just gives us another diffusion, and that will have scale function equal to the identity. And we say in that case that this is on the natural scale. So that's the role of the s here. And so sort of you can see that if s is not equal to the identity, then we can sort of understand the sort of this hitting formula of some kind of distortion of the real line according to the function s here. And so that's the role of s. Of course, that's just the hitting probabilities. It doesn't tell us about the time scaling of the process, and so that's contained inside the speed measure m. And so again, depending on your sort of knowledge about time change processes, basically what we're going to do to get the one-dimensional diffusion with this speed measure is just to time change the relevant Brownian motion by this this measure m. And so sort of precisely how we do that. So let's just think about things on the natural scale, just for simplicity for the moment. But yeah, what we do is we have a kind of a clock process here. So this is integrating the local times, or the occupation density of Brownian motion against the speed measure here. And so in particular, this is of course going to, well, if m is large in some region, then this is going to contribute a lot to this clock process when the Brownian motion is visiting that. And if m is small, it's going to contribute less. And so roughly speaking, well, what this is representing is the time that the time change process is spending up to time t of the Brownian motion. And so in particular, when the Brownian motion is in an area of large mass and we're moving more slowly, and vice versa. And so anyway, we define this kind of clock process, and well, to get to our time change Brownian motion, we're just going to invert this this process. So this is just the time of our time change process that we need to run the Brownian motion for to get our time change process to run up to time t. And so this, if you haven't kind of thought about one-dimensional diffusions before, you can take this as a definition of our time changed, or our one-dimensional diffusion. Okay, so that's kind of, like I say, sort of just general background. And just kind of very briefly, I want to kind of outline the scale function and the speed measure that we expect in the sort of scaling limit of our process. And so to do that, let's just start by looking at the random walk. And so again, let's try and compute our hitting probability. So for the one-dimensional case, this is when we're looking at only the nearest neighbor random walks. This is kind of an almost elementary exercise, just a gambler's ruin type exercise, to check that we can give a formula for this directly in terms of the nearest neighbor resistances. So in particular, just as the scale function here, these hitting probabilities were described in terms of these ratio of scale function differences, we can describe these ones in the discrete case in terms of these differences of nearest neighbor resistances between various sites. And so you'll see here that this Rn omega j omega k is just the nearest neighbor resistance from omega j to omega k computed according to the series law. So of course, if we just have these as our edge conductances, 1 over them is our edge resistances, and the series law tells us we should just add these up from site to site to give us the effective resistance from the endpoint to the endpoint of an interval. And like I said, it's just a simple gambler's ruin type problem to check that this is the right formula for this hitting probability. And so in particular, our scale function can be thought of as just being given by an appropriately signed version of the nearest neighbor resistance from omega 0 up to omega I. Of course, then we can just write this, each of these two terms here is just a difference between this function at omega I and omega j on the top, and omega j and omega k on the bottom there. Okay, so that's the scale function. And so just in terms of scaling limit, again, in the sort of nearest neighbor case, this is kind of almost elementary to understand the scaling. So in particular, if we look at the kind of tail of the distribution of our nearest neighbor resistances, then of course, if you remember, this is just e to the minus the distance between our 2 points. And so if I just kind of plug that formula in here, I can just write this down as something about the distribution of the distance between 2 points. And of course, for the Poisson process, this is just exponential, and we can compute this as being u to the minus rho. And so you can kind of now, from this formula, although it's kind of simple calculation, you can kind of now understand the role of the rho. So in particular, when rho is bigger than 1, of course, we have a mean for this quantity here. And so if we look at kind of sums of ID copies of something with a mean, of course, then this is going to scale linearly. But when rho is less than 1, of course, we're in a heavy-tailed situation, and we're not going to scale linearly. We're going to scale under the appropriate polynomial scaling to some Levy process, and so in particular to a subordinator here. So this is, of course, just a Levy process with positive jumps. And so what's shown on this picture is on the top here, this is just our Poisson points, and all I've done on the bottom here is just kind of plotted them according to this, their resistance from 0. So I don't know, maybe 0 is here on the picture. And so you can see that sometimes we're going to see a slightly long gap in our Poisson process. And when we exponentiate that, that's going to kind of well, be seen in the scaling limit. And in particular, these are going to represent somehow the jumps of the subordinator. That's the limiting processes here. And kind of, yeah, one of the sort of nice things is that exactly like I described, so for the Brownian motion, of course, if we actually look at our random walk pushed forward by our kind of scale function, so just this signed version of the resistance, then actually this becomes the martingale on this on this kind of deformed version of the space that we have down here. And so we have kind of nice ways to understand this. So in particular, it's just a continuous Markov process that's a martingale. It's just going to be a time change of Brownian motion, in fact, on this set that we see down here. And so that's kind of a nice observation in this case that's kind of exact in the nearest neighbor case. As for the kind of speed measure, this is very easy to describe, and this kind of describes why it's fine to consider the speed 1 version of the random walk, or maybe the just the process that jumps according to the conductances as their rates, because actually in both cases, if we study the invariant measure, then it's very easy to check that this kind of homogenizes. So in the nearest neighbor case in particular, you just got 2 edges, the conductance is bounded by 1, and so these are just bounded random variables. So of course they satisfy law of large numbers type behavior. And so if we kind of think about this as a measure, then this just scales to Lebesgue measure if we're kind of rescaling things in the appropriate way. Okay, so we kind of now have a guess for what our limiting process should be. So in particular, we kind of guess that we should be looking at a diffusion with a scale function given by some subordinator, a speed measure given by some, well, maybe constant multiple of Lebesgue measure. And it turns out that such a process exists. So of course, in the most classical works, like we're typically thinking of the scale function and the speed measure as being kind of smooth functions, but it turns out that we don't really need these restrictions. And so there's kind of generalized versions of one-dimensional diffusions studied by, well, various authors, but in particular, Ogura in the late 80s there has a paper where he gives a framework for describing such a process, or constructing such a process, I should say. But essentially, it's exactly as I described before. And yeah, actually, if we kind of think about how the scale functions and the speed measures converge, then naturally one would expect the scalings to appear as I've written down here. So just to explain this time scaling, so the n to the 1 is coming from the scaling of the measure here. and the n to the 1 over rho is coming from the scaling of the resistance here. And so that's the two factors that are contributing down here. And again, you can see that when rho is bigger than 1, the scaling of the resistance will just be linear. And so this will just give us our usual diffusive scaling. And so actually, I say this is non-rigorous. It's not so difficult to make this argument precise. And again, like just as for trees, there's kind of old results that tell you how if the scale function and speed measures of processes converge, then so do the processes. And so probably in this case, you could appeal to those. In the example I'm going to talk about, of course, we don't really have a strictly nearest neighbor model. And so these kind of classical results don't apply as given, although this is kind of the right heuristic for understanding the scaling limit. We need a slightly more sophisticated view to actually check this for the full version of the model. Yeah, so here's a simulation I meant to show you. So again, on the left here, we've got space along the bottom. The Poisson points to these gray lines. The slightly larger gaps here kind of map into very large gaps when we kind of plot them with respect to their resistance distance. And so just to describe the limiting process, so this is just a time change of Brownian motion on this kind of gray set. So time is running upwards here. So of course, it sometimes is going to reach a side of one of these big gaps, and Brownian motion will kind of wobble around here and then take time to cross it. So we're deleting the time that it's actually crossing it, of course. That's what the speed measure, having 0 speed measure on this part of the picture does. But anyway, this is just a time change of Brownian motion, and then we map back over here to get the scaling limit of the process. And you can see that this is not a Markov process. So in particular, at these kind of barriers here, there'll be times where, well, if you look at the hitting time of a barrier, say, then it's going to depend on which side the sort of Brownian motion hit it as to what happens in the future. So in particular, it would take some time bashing on the side of a barrier before it kind of crosses it. So maybe here, yeah, you see that it's sort of hitting the right, so the left-hand side, and then it crosses it, and then it's hitting the right-hand side of the barrier in the rest of the picture there. So this is what this limiting process looks like. And yeah, so this is like I say, a subdiffusive process. So yeah, maybe I've got sort of 10 minutes or so left, but and so yeah, I want to describe kind of the slightly more sophisticated view for that we're going to need for the full model. And so, as I kind of mentioned earlier, so this is going to depend on understanding the scaling of the resistance on the full network. And so here's the sort of result we can prove in this direction. So again, just to introduce kind of a quantity that, well, I guess if you haven't seen this definition before, it's not that helpful, but maybe just a reminder for people who have talked about these things. But anyway, we've got like a natural notion of electrical energy that we can define on our graph. So just given by this, so we've got our conductance multiplied by this difference here. So sorry, F is meant to be the voltage at which we're holding the vertices. Then if we hold the vertices at those voltages, then we dissipate this energy. So that's just kind of, I guess, a formula from kind of school level physics for energy dissipation on a network. And well, it turns out that we can describe the effective resistance in terms of this variational formula. So in particular, we look at the voltage difference, all the functions, or the volt. So we hold the vertices I and j here, say at voltage difference 1, and then we sort of look for the function that minimizes the energy over the network. So this will actually give us the voltage on the rest of the vertices in the network. This gives us the effective conductance between I and j, and so we take the inverse to get the effective resistance. So again, if you haven't met this definition before, this is going to be too quick, but this is like I say, the natural physical definition of effective resistance between these sites. And it turns out that this is a metric on the graph, and so this is quite convenient for us, as it kind of fits into the world of where we can understand its scaling limit using the sort of standard language of metric geometry. So indeed, things like Gromov-Hausdorff type topologies and so on. But yeah, just as a sort of first result. So again, this isn't really a precise version of his result, but gives you the sort of intuition. And what we can prove for our model is that actually we look at the effective resistance between two sites of order kind of n apart. Then just as for the nearest neighbor model, we can understand the scaling limit of this on the same scale in terms of sort of increments of a subordinator. And so, yeah, actually, like I say, this isn't really a precise version of the result, but this gives you a more or less clear picture of what the scaling limit of the resistance is. Maybe I don't have time today, but essentially the hard part of the story is just relating the full network to a sort of simpler nearest neighbor type model and kind of checking that the various approximations don't sort of mess up the story too much. So that's what's described here. And actually, for a more precise version of the result, and more accurate version of the result, like I say, this is a metric space. It's not necessarily just well, it's not kind of naturally isometrically embedded anymore into the real line, and so it kind of makes more sense to retain the information as the complete metric space here. And so what we're going to do is, like I say, rescale things in the appropriate way. Then actually we can describe the scaling limit as a kind of, again, a metric space. And so what the metric space scaling limit is going to be is just going to be the image of a subordinator where the distances here are measured with respect to Euclidean distance. And so exactly just the natural scaling limit of this picture is kind of given by an appropriate subordinator range down here. So anyway, so this is kind of the most important input really to the scaling of the random walks. And yeah, like I mentioned at the beginning of the talk, there's kind of nice machinery for studying random walks on trees. Sort of more generally than that, we can study the scaling limit of at least certain classes of random walks on random graphs, where we can kind of, well, actually follow kind of similar strategy to the proofs sort of used for trees, but like I say, replacing the sort of shortest path distance with the resistance metric. And so that's the result that I'm going to very briefly show you from this paper here. And so maybe I don't have time to describe in detail, and this slide certainly has too much to read carefully, but the basic objects that we kind of care about are kind of, well, let's say certain sets. So in our case, just the points in our point process, or maybe the vertices of the uniform spanning tree. We equip those with our resistance metric. So in both cases, I've described what those are and their scaling limits. We're also going to need a sort of invariant measure, or the speed measure of our walk. And so again, in both cases, this is some rescaled measure of, well, the invariant measure for the relevant processes. I'm going to have a starting point for my walk. And actually, because in both cases, I don't just have these spaces as abstract graphs, I have them embedded into some Euclidean space. I'm also going to allow for some extra quantity here that's going to map my kind of abstract graph into Euclidean space. So for the uniform spanning trees, this is just the map from the sort of graph tree into the relevant dimensional Euclidean space, or in my mop process, this is just, in a sense, the map that takes my point process with the resistance distance into the Euclidean space. And so that's what we're thinking about these objects. But anyway, in the case of the trees, or in these mop random walks, I can understand the scaling of these in some natural version of a metric space for well, metric spaces equipped with all of these various objects. And the kind of general result tells us that if we understand the scaling of these things, then we also understand the scaling of the stochastic processes. And exactly that's because somehow this resistance distance is telling us something fundamental about the, or characterizing something about the behavior of the walks here. And so this is the result that I can then appeal to in the mop random walk. And so, yeah, again, maybe I'm running a bit short of time, but exactly like the framework described there, I can kind of write down all the various objects on the space. So I'm thinking of kind of scaling space by 1 over n. The resistance scaling is n to the 1 over rho. The measure scaling is n to n inverse here. And like I say, my sort of embedding is just given by my sort of, you can think of this as the map from this kind of deformed resistance space down here into Euclidean space. And of course, like I say, in the kind of full version of the mop random walk, of course, this metric space here is no longer kind of isometrically embedded into Euclidean space. It's kind of living in some sort of abstract space of metric spaces. But anyway, the sort of naturally associated stochastic process with these kind of resistance metric is exactly our mop random walk. And again, this is kind of too much for the time I've got here, but there's kind of a natural way to describe the limit here in terms of the range of a stable subordinator. And there's also a natural way, when I should say, when we've got a resistance space to associate with it a process. So just as I can do that in the discrete case, so in the discrete case, the resistance metric actually characterizes my conductances on my network, and that gives me my random walk. It turns out I can do similarly in the continuum case, and in particular, the kind of natural process associated with this resistance space is the process I wrote down before. So just this Brownian motion. Also, the one-dimensional diffusion with speed measure given by the subordinator, and scale function given by the subordinator and speed measure Lebesgue. And while I have the convergence of the discrete spaces to this, and so as an immediate kind of consequence of that and the sort of general result I just said, then I get the conclusion that I wrote down before. And so I see this same scaling limit for the processes. Yeah, that's kind of basically, I guess, where I can stop. So I guess just to sort of finish with a few little pictures. So I should say this kind of idea in some sense, or the theory of studying processes via their resistance metric, a lot of the work to get to the sort of current point of knowledge was done in the, or was motivated by understanding random walks and diffusions on fractals. So in particular, the sort of notion of a resistance metric on a general space was introduced by Kigami to study kind of random walks on things like Sierpinski gasket type graphs and their convergence to Brownian motion on the limiting space. Yeah, so I've described kind of there's nice work, particularly in the case of trees. So maybe for things like critical Galton-Watson trees, I think the ones shown here. The results naturally apply there, of course, because the distance, if we understand the scaling of these as in terms of their kind of usual distance, then this is immediately telling us about the resistance as well. So here, I think, like I say, these are critical Galton-Watson trees. This one's here, the uniform spanning tree. Yeah, closely related, this is a critical Erdős-Renyi graph. So again, this is something like the critical Galton-Watson trees, apart from we have some finite number of loops in here, but that's not enough to destroy our understanding of the resistance scaling. And another model that turns out to be well suited to studying things by the resistance metric is the model of loop trees. And so actually the result of Eleanor Archer, who I think was also in the audience here, showed again there's kind of some natural version of discrete version of loop trees for which we can understand the scaling limit via this resistance type approach. Anyway, I guess that's the end of my time. So yeah, I will stop here. So thank you for listening.
Thank you very much for the very nice talk. Are there questions? Yes, usually you can just ask directly or write something in the chat.
Okay, then I have a question for you, David. Hi. Does that give you any information on the way the diffusivity vanishes when you're approaching the critical value rho equals 1?
So you mean, okay, so we're just studying a regime where we're not diffusive. So I guess the answer is no. But I suppose, like, if you take the scaling limit of these processes as rho goes up to 1, then these processes will just converge to Brownian motion. So in that sense, we can interpolate from our regime to the diffusive regime.
Which would mean that there is no intermediate scaling, right? That there is no other limit arising when you are.
No. So I think exactly as rho goes to 1, then our subordinator will just converge to like a straight line, and then, of course, this is just telling us that the resistance is just becoming, the usual resistance. So yeah, I think there's no.
Well, you can exchange the two limits, right? That's what you say.
Mm-hmm.
The scaling limit with the limit when rho goes to 1, you can play with these two limits as you want.
Yeah. Well, so yeah, I don't know about exactly studying the kind of interplay of the limits together, no. But I think at least for the limiting process, unless you take rho to 1, then this will give you the Brownian motion. I think for like in the other direction, like coming down from above, like so going from diffusive to subdiffusive. I mean, I guess this relates to work of Alessandra, where she studies how the diffusion constant goes to 0, right? according to the various parameters in your model. So I guess that's
correct. But Alessandra's work was I don't know. I mean, I know about the results in in dimension larger than 2.
Okay. Yeah, I think, well, the paper, like I mentioned, like this 2009 paper, I think well, Alessandra, if she's still here, can correct me if I'm wrong, but I believe they kind of give characterizations of the diffusion constant there.
Yeah, so you can do this, you can do. But once you have the characterization, there is still some work to do to analyze from I mean, you get a variational formula, but then you still have some work to do if you want to know how it behaves with the temperature.
Yeah, sure.
With the density. And there are some, let's say, conjectures.
Exactly. So she also, of course, in that paper, like also studies with like exactly like the effect of the temperature and so on. And so, yeah, in our results, I should say that we do allow like a fixed temperature, but we don't study particularly the role of this. So of course, this will have an impact on the constants that come out, but yeah, we don't at all kind of study the role.
No, but it doesn't mind. I mean, okay, forget about the temperature, and you can just focus about the way the diffusivity behaves in terms of the density. And that makes sense. And that's a question, but that's a question you can ask even in high dimension. And I'm not sure about the results in one case, but okay.
Yeah, no, it's a good question. Yes. But I think, like I say, at least for the limiting process, you just have this kind of easy convergence of the Z rho to the Brownian motion as rho goes to 1. I don't know, like you say, if you can, what would be the right kind of regime to see that from the discrete processes directly? Yeah.
Okay, but I just say, okay, that would be the other way when you're going from diffusive to subdiffusive. So.
Yeah.
Thanks.
Okay, well, thank you for the question.
Are there further questions?
I would again have one, if possible. Thanks. In terms of extensions to random graphs and trees that you showed at the end, say the fractal trees that you've shown, are there any limits, or could this be extended to any random graph and tree and any metric topology?
Yeah, so I mean, okay, so yeah, like it's a good question. Thank you. So of course the answer is no. It can't be extended to anything. So yeah, actually, so we need to understand the scaling limit of these resistance metric spaces, but the strong condition here is that we want the limit to also be something called a resistance metric space. And so in particular, this is kind of the definition is here. So this is kind of the generalization of resistance metric to an arbitrary set. And so basically what it is just a metric where if we take any finite set, we can find a weighted graph which represents, whose conductances kind of give us the effective resistance restricted to those points. And this is a very strong condition. So just to give you an example, so here were the examples I had. So kind of it's very easy to see that this is true for like one-dimensional Euclidean or things like shortest path metric on a tree, but actually it's not true for higher dimensional spaces. And in particular, then the resistance metric just sort of degenerates. It doesn't give us, it's not going to give us the right information about the stochastic processes anymore. But yeah, so there is kind of an intermediate regime. So in particular, like I say, this was a lot motivated, the study of resistance metrics by random walks on certain classes of fractals. So in particular, sort of low dimensional fractals, I would say. So things like the Sierpinski gasket. If you sort of, for example, start with graphs and put on like conductances 1, 1, 1 here, you kind of copy that over here, but kind of rescale things by 3/5 and iterate, then this gives you a metric. This kind of gives you a consistent sequence of metrics. And so this gives us a resistance metric on our limiting space. And this is going to correspond to kind of a natural process on the limiting diffusion, which is called Brownian motion. But yeah, somehow in the stochastic process point of view, the kind of non-degeneracy of the resistance metric in the limit is basically something like the point recurrence of the process. So this is of course a very strong condition. So of course, for like Brownian motion in 2 dimensions, we know that this doesn't hit points, and this is basically a equivalent property to saying that the resistance metric is, well, degenerate in that case. So yeah, somehow the classes of examples to which we can deal with are somehow kind of low dimensional in a certain sense. So yeah, I guess it's a natural question and a very good question as to whether you can kind of generalize a result like this. What's the kind of right potential theory? So somehow the resistance metric is capturing the occupation density of our graph, so some kind of potential density. And so, yeah, one can imagine that if you can kind of prove appropriate convergence of potential densities in arbitrary spaces, then you'll get convergence of the stochastic processes associated with these. But yeah, the problem is, of course, checking the conditions, and somehow in the world of resistance metrics is quite often a very natural thing to study for various examples of random walks on graphs, and so that's why it's useful in the examples I've studied here. So yeah, in answer to your question, yes.
Okay, thank you. Yes, more than
by no means
all. Thank you. Thanks.
All right. I would say I would thank both speakers again, and very nice talk. And if you have questions, I'm